Miss Often, and this video will let you learn about shortcuts to triangle congruence. Let's get started. Our objectives today are to be able to apply the following to construct triangles and solve problems, as well as to prove two triangles congruent. We have 5 postulates or theorems. Those are SSS, side, 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 SAS, side, angle, side, ASA, angle, side, angle, and AAS, angle, angle, side. We also have hypotenuse, leg. In lesson 4.3, the previous lesson, you proved triangles congruent by showing that all 6 pairs of corresponding parts were congruent. But there's a property called triangle rigidity. It gives you a shortcut for proving that two triangles are congruent. So it states that if the side lengths of the triangle are given, the triangle can have only one shape. And you saw this in the Desmos exploration today. This leads to the postulate of side, side, side congruence. So you only need to know that two triangles have 3 pairs of congruent corresponding sides. So here's our postulate, side, side, side congruence. If 3 sides of one triangle are congruent to 3 sides of another triangle, then the triangles are congruent. So if we're given that AB is congruent to DF, BC is congruent to DE, and AC is congruent to EF, that is enough information for us to draw the conclusion that triangle ABC is congruent to triangle FDE. Please note that we do have to write the letters in the correct order. So since AB is congruent to FD, and F and A are corresponding angles in this case, they must both be written first. Here's a new vocabulary term, an included angle. An angle that is included is an angle that is formed by 2 adjacent sides of a polygon. So in this diagram, angle B is the included angle between sides AB and BC. This leads to another postulate, side, angle, side congruence. If 2 sides and the included angle of one triangle are congruent to 2 sides and the included angle of another triangle, then the triangles are congruent. So we see here that angles A and E are included angles. A is included between sides AB and AC. E is included between sides ED and EF. Additionally, AB is congruent to EF and AC is congruent to DE. This gives us the SAS congruence statement. Triangle ABC is congruent to triangle EFD. What I find helpful in writing these congruent statements is starting at the included angle, traveling along one of the congruent sides to another angle, and then to the third angle, which should be at the vertex of the other included side, and using that same pattern to write my congruent statement. So I go from A to B along a congruent side, then along a not marked side to C. Similarly, I go from E to F along that side with 1 tick mark and along a not labeled congruent side to point D. This gives me ABC is congruent to EFD. Please be cautious. The letters SAS must be written in that order because the congruent angles must be included between the pairs of the congruent corresponding sides. We also can have an included side. This is the common side of 2 consecutive angles in any polygon. So the next postulate is going to use the idea of an included side. Right here we see side PQ. That's the included side of angles P and Q. So keep in mind the SAS postulate is going to guarantee that if you are given the lengths of 2 sides and the measures of included angles, you can construct one and only one triangle. We are going to see a proof with that in action right now. So here I am given that these 2 opposite sides are parallel and congruent BC is parallel to AD. BC is also congruent to AD. So we want to prove that ABD, which is this triangle here, is congruent to CDB, this triangle right here. So let's get started with that. We start with our given statements. BC is parallel to AD. This leads us to the conclusion that CBD is parallel to ADB. That's this angle here on the upper left and this angle on the lower right. That is the alternate interior angles theorem, or PAI. We also have BC is congruent to AD. That was another one of our givens. Lastly, we have the reflexive property that BD is congruent to BD. And now, because we have that labeled and we have the congruent angles here, I have my side, angle, side, again, side, angle, side. So I can say that ABD is congruent to CDB. Okay, please notice that I am traveling from one not marked as congruent angle to another not marked as congruent angle, and then along the congruent shared side, both times when I name the triangle. So there's my final statement, and I'm going to say SAS, which was through steps 2, 3, and 4. Our next congruence, and this should be ASA, not SAS, it should be ASA congruence, angle side angle. If two angles in the included side of one triangle are congruent to two angles in the included side of another triangle, then the triangles are congruent. So you'll notice here that I have A and C with the included side AC. I have D and F, the included side DF. So a lot of times when I name these triangles, I would probably start with ACB, just make my life a little bit easier, and then go DFE, going from my congruent angle to my other congruent angle, and then from corresponding to other corresponding, and then ending with my not yet labeled third angles. But that's a choice that these people have made. They did ABC, and that would be congruent to DEF in this case. We can use the third angles theorem to prove another congruence relationship based on ASA, and this theorem is angle-angle side, or AAS. So here I see I have two angles labeled and then a non-included side. And similarly on my other triangle, I have two angles and a non-included side, but they are corresponding to each other. So I have GHJ is congruent to KLM, and I am naming my corresponding sides, or I'm naming my corresponding angles, then my not labeled corresponding angles, and then my labeled with two arcs corresponding angles to get that congruent statement of GHJ is congruent to KLM. And again, this is angle, angle, side. Let's see a proof of this here. So I'm given that G is congruent to K, J is congruent to M. That means by the third angles theorem that H must be congruent to L. I'm given that HJ is congruent to LM. And so I have angle side angle right here, which I was previously using as a postulate, and therefore the two triangles must be congruent. So that proves that angle, angle, side congruence must work if we accept angle, side, angle. Our last type of congruence is hypotenuse leg. This proof will be done as a separate video and is available in the Google Classroom. It states that if you are given a right triangle and you know that the hypotenuse and one of the legs are congruent, then to the hypotenuse and leg of another right triangle, then the two triangles are congruent. And as we can see here, triangle ABC is congruent to triangle DEF. Now, there is hypotenuse leg because that is a special case of side-side angle, which in general does not hold, but we do not have leg-leg congruence in a right triangle because that really is just another case of side angle side. So we really don't need to have it. Okay, so looking at a couple of these, we see right here on 3 and 4 that we can prove that these triangles are congruent by side XZ and ZV, angle, the vertical angles XZY and VZW, and side, ZW is congruent to ZY, so that's a side angle side. We have another side angle side here example in number 4 with the shared side at BC and the reflexive property. Please note with number 1, we have nothing because we do not have corresponding angles. So that just does not work out for us. This angle is not included on the left hand or the right hand triangle, but it is an included angle between the two congruent sides on the left hand triangle. So that's none. And 2 is an example of side, side, side with our shared side right here and the reflexive property. Okay, another one here, postular theorem to prove the triangle's congruent. Number 1, I hope you are thinking angle, side, angle. In problem number 2, you could say side, 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 but you could also say hypotenuse, leg. And for number 3, we could say side, 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 or we could say side, angle, side. You also could say hypotenuse, leg here, though if we don't know that these angles are congruent, that's not really going to work out so well for us. But knowing that our angles, we have some vertical congruent angles here, that does get us to side angle side. I hope this has been helpful for you as an introduction to the various ways of proving that two triangles are congruent.